Hi everyone, more fun with functions. In section 1.10, we're going to talk about difference quotients, which relate to average rates of change. These ideas will relate directly to section 1.11 on derivatives, which is a key topic in calculus. So what is an example of a difference quotient? Well, the most common geometric application is that it's the slope of a secant line. So let's say that you have a function f. We have here the graph of y equals f of x. It's a nice graph, no weird jumps or breaks or anything. Take two distinct points on the graph, a comma f of a and b comma f of b. Remember, function values correspond to y coordinates. Connect the dots. The line that connects these 2 points is called a secant line. And the slope of this secant line has an important application. The slope of this secant line gives the average rate of change of the function f on this interval from x equals a to x equals b. Assume for now that b is greater than a. Average rate of change is given by the slope. What slope? Rise over run. The rise is f of b minus f of a. The run is b minus a. In principle, b could even be less than a in this formula. B could be here, a could be there. Rise over run. Now look what we have here. Why is this called a difference quotient? Because it's a quotient of differences. On the top, we have a difference of outputs. On the bottom, we have a difference of inputs. Change in y over change in x. Change in outputs over change in inputs. A difference quotient. A common application of difference quotients is average velocity. Average velocity is perhaps the most important example of an average rate of change. So for example, let's say you're in the movie Speed. You're Keanu Reeves or Sandra Bullock. And the villain, Dennis Hopper, says, okay, hotshot, here's the deal. Wherever you are, we're going to call that the 0 milestone. You're at position 0, at time t equals 0. Let's say noon. Now here's your task. You must travel 100 miles due north in exactly 2 hours. So exactly 100 miles in exactly 2 hours. If that's the case, what does your average velocity have to be in order to accomplish this task? All right. Average velocity on this time interval is given by change in position over change in time. Position is often denoted by s. Change in position, delta s, over change in time, delta t. And by the way, it's change in position over change in time. There's a high school teacher in North Carolina who was angry at physics textbooks for saying position over time. No, it's change in position over change in time. Because we don't care if this is happening in California or New York or Utah. What matters is the change in position. And it doesn't matter if it's happening on a Sunday, a Monday, a Tuesday, or for that matter, if you're starting at noon or at 1 p.m. or 2 p.m. What matters is the change in time. The average velocity is given by the change in position over the change in time. The change in position is given by s of b minus s of a, s of a. Your position at the end time minus your position at the beginning time over the change in time, b minus a. So here, the average velocity from noon to 2 p.m., your position at 2 p.m. is at the 100 milestone, the 100-mile milestone, minus your position at time 0, noon, is the 0 milestone, all over 2 minus 0, that's 2 hours. From noon to 2 p.m., the change in time is 2 hours. So the difference quotient here is given by 50, and the unit is given by basically the y unit over the x unit. Here, it's the s unit over the t unit, the unit of position over the unit of time. Unit of position is miles. Unit of time is hours. So it's 50 miles per hour, or 50 mph. Remember, the unit is given by the top variable's unit over the bottom variable's unit. All right, 50 miles per hour. It makes sense. In order to travel 100 miles due north in exactly 2 hours, your average velocity must be 50 miles per hour. So what are some strategies? Well, assuming that you have a clear road that's going due north, you can go steadily, 50 miles per hour, go at a constant velocity. Or maybe you start off slowly and then you realize, uh-oh, I better speed up near the end, so I hit that 100 milestone at 2 p.m. Or maybe you panic, you start off going really fast, you might even overshoot and then go backwards. Over here, the velocity would be negative, by the way. Still, the average velocity would be 50 miles per hour. It's the slope of the secant line between the point 0, 0 and the point 2, 100. Remember, at time 2 p.m., you better be 100 miles due north of the starting point. Now, there's a theorem in calculus called the mean value theorem for derivatives. So here's the idea. Let's say that Dennis tells you, all right, hotshot, here's the problem. As you're accomplishing this task, there's a bomb on the bus. The bomb will go off if the bus ever hits exactly 50 miles per hour as instantaneous velocity. So if the bus ever hits 50 miles per hour on that speedometer, the bomb will go off. How should you feel? Very badly. Because unless there's a gap in the road or something, and there is in the movie, but unless there's a gap in the road or something, yeah, if the average velocity is 50 miles per hour, and if there are no gaps or anything, then at some time in here, at some time point in here, the instantaneous velocity will have to match the average velocity. In other words, your speedometer will have to hit 50 miles per hour at some time in here if you're going to have an average velocity of 50 miles per hour. Graphically speaking, at some time in here, the tangent line, this line that models the graph locally, the tangent line must be parallel to the secant line. They must have the same slope. Here, the instantaneous velocity is 50 miles per hour. That's the slope of the tangent line. Here, the slope of the secant line is the average velocity, 50 miles per hour. If these slopes match, the bomb will go off, you're in trouble. That's from the mean value theorem for derivatives. Next, what are some forms for difference quotients and how do we evaluate or simplify them?